Ernest Rutherford, in his presidential address to the Royal Society in 1927, said, "It has long been my ambition to have available for study a copious supply of atoms and electrons which have an individual energy far transcending that of the alpha and beta particles from radioactive bodies."
What he was asking for was a particle accelerator. And fast forward to present day, we now have tens of thousands of them all over the planet. Most of these accelerators are smaller scale machines used for applications such as cancer radiotherapy. But for pure high energy physics research, we need these accelerators to be on a much grander scale.
Located at CERN, on the border of Switzerland and France, is the largest particle accelerator in the world, the Large Hadron Collider, the LHC, which circulates protons around its 27-kilometre circumference. At its core, the physics of particle acceleration relies on electric fields. In the most simple case, a charged particle, like a proton or an electron, will receive a push if placed inside an electric field. The technique becomes a little more complicated when accelerating particles inside a machine such as the LHC. Here, scientists use specifically shaped metallic chambers called radiofrequency or RF cavities. Oscillating electromagnetic fields are used in vacuum inside these cavities. By precisely timing a bunch of charged particles with the oscillations, we can ensure they always see the accelerating component of this field and get the maximum push through the cavity.
The LHC was groundbreaking for modern particle physics. It proved the existence of the Higgs boson in 2012, contributing to our understanding of the origin of mass and ultimately resulting in the Nobel Prize for Physics in 2013. Now, scientists are looking to the next generation of particle accelerators, proposing even larger machines operating at even higher energies. The circular accelerators actually limit the maximum energy your accelerator can reach. When you send a particle round a bend,
typically done via dipole magnets designed to steer its path, the particle radiates away some of its energy. This is called synchrotron radiation.
What's worse is that lighter particles suffer from this effect more than heavier ones, which means future circular accelerators, hoping to accelerate light particles like electrons and positrons for their cleaner collisions than protons, will always be limited in their maximum energy because of this effect. So ideally, we'd keep the electrons in a straight line. But at first glance, this design also seems inefficient, as they can only pass through a cavity once. They can't be reused for collisions like in a circular machine. We could increase the strength and therefore accelerating gradient of our cavities, but even these are limited by breakdown of the metallic walls. Make the fields too strong and the inside of your accelerator is going to spark. So what we want is a way to accelerate particles to very high energies in a straight line and over a short distance. In other words, with the maximum accelerating gradient. And it is at this point that physicists look to a fundamental redesign of the accelerating technique itself.
We can overcome the limitation of cavity breakdown if our choice of accelerating material is already broken down. And what better choice than the fourth state of matter, the most abundant in the visible universe? We call this plasma. Imagine a gas, a collection of neutral atoms that are free to move around. If we give this gas enough energy, we can excite the atoms so much that they kick off some of their electrons. They break their bonds. This gives us plasma, a sea of delocalized electrons around positive ions.
So how is this useful to us? Well, when you separate charges, you create electric fields, which, as we know, is exactly what's needed to accelerate charged particles. The idea of using plasma to accelerate particles was first proposed in 1979 by Tajima and Dawson. They suggested you could use a laser pulse to drive waves, or Wakefields, in a plasma, which you could then trap electrons inside of and accelerate them to very high energies.
Thanks to the later invention of chirped pulse amplification in the 1980s, laser pulses were able to be compressed into record-breaking short and intense pulses. This achievement was awarded the Nobel Prize in Physics in 2018. As this short laser pulse moves through the plasma, it exerts a force on the plasma electrons known as the ponderomotive force. This pushes them away, creating a cavern of only the heavy, and thus comparatively static, positively charged ions. The imbalance of charges causes the space charge field to drag the plasma electrons back to their original positions. The electrons overshoot, repeating this process and creating a period of oscillations, a plasma wave travelling in the wake of the laser pulse.
In the early 21st century, this technique really began to take off. By precisely timing the injection of electrons, which we call the witness bunch, into the plasma wave, they were accelerated to very high energies over just a few millimeters, whilst also preserving the quality of the accelerated electron bunch. You can think of this very much like surfing. Imagine you have a lake. This is your plasma. As a boat drives over the lake, it's going to create waves behind it as it drives. This is very much like a driver creating Wakefields in a plasma. Now, a surfer could ride one of these waves if they precisely timed when they jump onto the wave. And that is very much like the injection, capture, and acceleration of electrons in a Wakefield. The challenge with laser Wakefield acceleration is scalability. As it travels through the plasma, the laser pulse, and therefore its generated Wakefields, travel slower than they would in vacuum. The witness electron bunch, traveling close to the speed of light, quickly catches up to and exceeds the velocity of the Wakefields. This means the electrons effectively slip, and you no longer have effective acceleration. So the alternative approach is to swap out the laser pulse for something else. By using another charged particle bunch to drive the Wakefields, the witness electrons would no longer overtake. Then we have two relativistic charged particle bunches, which means two groups of particles all traveling close to the speed of light, as both the driver of the Wakefields and the witness. The velocity of these charged particle bunches is not really affected by the presence of the plasma. Let's bring this back to the idea of surfing by thinking about the witness velocity. The physics of beam-driven Wakefield acceleration allows the beam to stay at the same part of the wave.
You can see this when a surfer directs themselves perpendicular to the direction of the wave's velocity. They're able to ride the wave for longer. With laser-driven Wakefield acceleration, the witness bunch slips into a different part of the wave, similar to how our surfer here is changing their direction to now be parallel with the wave's velocity. The surfer, our witness bunch, now catches up to and overtakes the waves, causing them to slip and no longer effectively accelerate.
The more energetic your drive bunch of particles, the greater the distance over which you can drive strong Wakefields in a single stage. This also means you can transfer more energy to your witness bunch. Now, we know that CERN offers the highest energy particles in the world. Protons are sent around its vast accelerator complex for use in a variety of experiments. The opportunity to use this beam facilitated the world's first proton-driven plasma Wakefield acceleration, a technique performed by one experiment in the world, the Advanced Wakefield Experiment, AWAKE.
We begin by travelling roughly 60 metres deep underground through the tunnels of the CERN accelerator complex.
The AWAKE experiment drives its Wakefields with protons extracted from the CERN superproton synchrotron. These protons leave the SPS at 400 GeV, travel down this tunnel for roughly 800 meters through a series of magnets that are designed to keep them tightly packed together and on the correct trajectory.
A high-power laser is used to create the plasma by ionizing a 10-meter column of rubidium vapor. Just before awake, at the end of the SPS transfer line, our laser joins the protons, and together they co-propagate towards the entrance of the awake vapour source. In order to effectively drive Wakefields in a plasma, the driving particle bunch should have a length on the order of the plasma wavelength. This is on the millimetre scale in the awake case. However, the proton bunches we get at CERN are much longer than this, approximately 8 centimetres. Compression of the proton bunches is not possible in practice, but thankfully it's the plasma itself that saves the day here. When the proton bunch enters the plasma, you still get an initial, albeit weak, Wakefield. In some regions of the Wakefield, the force transverse to the protons is focusing, and in other regions, defocusing. This means that as the long proton bunch travels through the plasma, some of the protons are periodically concentrated together, whilst others are blown outwards. Eventually, the long proton bunch is cut into a series of shorter microbunches, the separation of which aligns pretty well with the plasma wavelength. This is called the self-modulation instability, and what you're left with is a train of short proton bunches able to drive effective Wakefields in the plasma. The occurrence of this process was confirmed experimentally in the first run of Awake, opening the door to acceleration experiments. By shining a UV laser pulse onto a cathode, we excite electrons via the photoelectric effect. We then bunch them and transport them along the electron line via a complex series of magnets designed to correct, focus, and bend the electron bunch to the main beamline. We precisely time the injection of the electrons with respect to the laser and protons to ensure we have the best chance at capturing and subsequently accelerating our electrons in the Wakefields.
In order to measure the energy gain of our accelerated electrons, we use a magnetic spectrometer after the plasma cell. Here we use quadrupoles to focus our electron bunch horizontally and vertically. We then separate the electrons from the protons with this dipole, which steers our electrons through a magnetic field, and the electrons appear at the end of the spectrometer line on this scintillator screen, where the position of the electrons on the screen tells us the energy at which we accelerated them.
In 2017, Awake demonstrated electron acceleration for the first time, achieving a maximum energy of 2 GeV over 10 meters. The electrons were over 100 times more energetic than when they started. Over the last decade, the Awake experiment has gone from strength to strength. We've upgraded our plasma source, where we're currently studying the effects of steps in the plasma density and what impact these may have on the amplitude of the Wakefields. We continuously test and develop our diagnostics to shine light on the instabilities of plasma. Upgrades to the spectrometer have revealed for the first time in Awake high-resolution images of accelerated electrons. This allows us to assess the quality of the bunches we accelerate. In parallel, we research and develop new plasma technologies for the future of plasma acceleration, where we will look to scale up to longer accelerators.
In order to continue to advance particle physics, we must advance our accelerator technology alongside it. Studies of the complicated dynamics of plasma and its limitations are a necessary step. Facilities like Awake serve as a proof of concept in the hope that we can unite plasma physics with accelerator science.